delay. Let me just start. So as Ritubrata mentioned, so this word quantum, I mean, for today, this will mean that this is sort of synonymous for non-commutative and possibly infinite dimensional. Well, I mean, I have not, I mean, as of now, I didn't say, I have not mentioned what is non-commutative or what is infinite dimension. I mean, because infinite dimension, there has to be something of infinite dimension type, meaning vector space or algebra or something. Non-commutative again goes for algebra or group, anything. I mean, so I have not, I mean, this is just a vague dictionary, which is, of course, I mean, at the moment, it looks quite awkward maybe as a mathematician, but okay, let's this is just a broad idea. And by the way, today all I'm going to do is I'm going to talk about mostly quantum permutation group, and later by the end of the talk I will actually show how quantum, sorry, I will talk about permutation group, classical permutation group, sorry. And then in the end, I will actually give you a glimpse of what is the meaning of quantum permutations or quantum permutation group, which essentially means what is quantum symmetry of finite spaces. So most of the things, again and again, it will be done for finite set and permutation group. So if you have any question, feel free to stop me and ask me, ask me at once. So let n is a positive integer and consider xn to be a set that contains n points. Now, what is the symmetry of this set? What is the meaning of symmetry? Symmetry vaguely means that given an object means in this case the object is the set xn, and you are a symmetry is a map from that object to itself. In this case, this will be a map from xn to itself, which will preserve certain property. In this case, the property is, let's say, I mean, in this case, the property that we are interested or I'm interested in is the cardinality. So that means, so being said that the symmetry of xn is a bijection from xn to itself. Why? Because first of all, it's a map from xn to itself and it preserves the cardinality, as you know, since it's a finite set, so therefore it's a 1, 1 and on 2, so it has to be a bijection. Now, a symmetry of xn is so maybe I should say asymmetry. And now, if you consider symmetries of xn, this is not a standard notation, by the way. I'm just writing it for the sake of motivation. Symmetry of xn, that means f from xn to xn such that f is a bijection. And now, you know, this is from your first year or second year mathematics course, I mean BSc mathematics course, that this forms a group symmetry. So maybe 1m is sufficient. xn is a group with respect to composition identity element for this composition of maps. So that means well, essentially, you know, this is something I'm probably going too much backward. Backward means too much element at the elementary level. So this is basically a group, symmetry of group, and this group is basically known as permutation group. So sim xn is basically nothing but Sn, actually isomorphic to Sn. And what is Sn? Sn is basically, so this is basically sigma, where sigma is a permutation on n symbols. So basically, given any function, now why this is true? This is basically saying that given any function on xn, this function is determined by its value. So let's say if x, so that means you know the function if you know what is f1, f2, and so on and so forth, and that essentially gives you a permutation. Meaning, let's say if 1 is going to 2, 2 is going to 3, 3 is going to 4, and so on. That is the permutation on this side, which means that that set of all bijections on xn gives rise to something called the permutation group. And also it is easy to check that the composition of permutation is same as basically the composition of these functions. So this is basically the same thing, but for the sake of just like motivation or differentiating between these two objects separately, I just mentioned this. So okay. So this is more or less the rough idea of permutation group, and this has some universal property, meaning that if there is any group which acts on, so okay, now Sn acts on Xn. Before I proceed, let me just quickly ask you, how many of you are familiar with group actions? I mean, if there is anyone who doesn't know what is a group action, please let me know. So everybody is familiar? Okay.
Someone said he doesn't know, maybe.
Sorry?
Yeah, someone said he doesn't know.
Oh,
Actually,
sorry,
those who are from second year, they don't know.
I see. Okay, fine. It's okay. I mean, it is not necessary. I don't. So okay. That's basically Sn acts on Xn. What exactly this means? You don't need to know what is a group action. If you know, this is fine. If you don't know, let me just explain this. So this is something like, it's a map from Xn cross Sn to Xn. It's just a map. What actually it does, it is defined by, you take a point from Xn, say I, and you take a permutation from Sn, say sigma, and then this map is defined as, you just evaluate sigma at I. That means the value of alpha, this tuple I sigma, goes to sigma I, and this is basically, you can take this as the definition of action of the permutation group on Xn. Okay. Now there are some more properties of this. So for instance, if you take alpha, so now the question is, on this side you have a group. So the question is how this map behaves with the group operation. So this is a simple computation. So if you take two permutations, sigma 1, sigma 2, so I is from Xn and sigma is from Sn. Now if you take two permutations, sigma 1, sigma 2, then this is by definition, this is sigma 1, sigma 2 of I. Sorry, sigma 2, 2 of I. Now this is alpha of sigma 2 I, comma sigma 1. And then this is alpha of how do I write this? So this will be alpha of I sigma 2, comma sigma 1. So that's how this behaves. So if you compose two permutations here, then this is basically you first apply this and then apply this. So this is basically the property of group action. So often actually this is written as alpha. So actually let me just see. Yeah, it's fine. It's fine. So that's how this group, I mean, this is basically the meaning of action of permutation group on Xn. Now what I am going to do is I am now going to consider this notion of permutation group and its action on Xn in a different way. The same thing, the same idea, same object, everything will remain same, but I will just replace everything by something else. So what am I going to do is now we are going to replace Xn by C of Xn. This is basically algebra of functions, continuous functions on Xn, but in this case continuity is redundant because X is finite set, so it's like it's a equipped with the discrete topology, so everything is continuous. And Sn by C of Sn, this is again also functions on complex valued functions on Sn. And finally, since we had this object, this Xn cross Sn, we also replace this by Xn cross Sn. Maybe call it some function L. I mean, this is probably not the good notation, but okay. Okay. So basically what we are doing is we are going to replace sets by function. Sets by algebra. Like Xn by C of Xn. But this Cxn has some specific. In general. Now let us try to exploit the properties that the C of Xn, C of Sn, or C of Xn cross Sn has. So so since we are dealing with finite set, so I will stick to finite. So for any finite set X, C of X is a vector space. Number one, it's a vector space over C because you can add pointwise addition and so on and so forth. And second thing is C of X is an algebra, meaning for F1, F2 in C of X, you can define F1, F2 on X is basically F1 of X times F2 of X. So that means if you take two elements from C of X, you can define their product, and this is called pointwise multiplication. And it is an algebra, and C of also it has an involution, meaning if for all f in C of X, f star in C of X defined by f star of X is fx bar. So it is like conjugation, like for a complex number, you have a complex conjugation. For a complex valued function, you can also define sort of complex convolution. This is called involution. And it is also unital. That means if you consider the function which takes all the elements to 1, that is unit element. So this is actually the unital star algebra. So for any finite set, this is true. So therefore, these objects, C of Xn, C of Sn, C of Xn cross Sn, they are all unital star algebras. Okay, and moreover, since they are finite dimensional, so you can, there is something more. There is something more means you can still define a norm on this, and you can make it a unital star algebra, Banach star algebra. In fact, it's a unital C star algebra, but that is not necessary at this moment. So so far we are okay with these three properties actually. So now what we are going to do is, now what we had is, we had just maps from Xn cross Sn to Xn, and this is just a map, and since Xn and Sn both are finite, so this map is automatically continuous. So we had continuous map from Xn cross Sn to Xn. Now we want to understand this map alpha, but at the level of algebras. So for that matter, what we have to do is, so alpha gives rise to a map alpha tilde from C of Xn to C of Xn cross Sn. And I have to define this map. And how this map is defined? So alpha tilde, now alpha tilde takes a function from C of Xn as an input, and then this thing will be an element here. That means it is a function on Xn cross Sn. So what I do is, I just take an element I and sigma, and then I define it to be sigma inverse I. So once again, this map alpha was what? You take a tuple I sigma and you send it to sigma I. That was the map. Now here, using that map, I am defining at the level of function. So alpha tilde is defined in the following way. Again, alpha tilde takes a function as an input. So alpha tilde of f will be here, which means it's a function on Xn cross Sn. So you evaluate this function at I sigma and you define it to be f of sigma inverse I. So at the moment, this is just a function. Okay. Now, what are the other properties that we have for this function? Now, this is okay. By the way, for the okay, that's how this function alpha tilde is defined. But now observe one thing, that now let us exploit these properties of C of Xn. C of Xn is a vector space. X is a finite set. C of Xn is a vector space. and xn has n many points. Therefore, C of xn is a vector space of dimension n. How? It is very easy. So C of xn is spanned by this delta of delta I functions, where I is in xn. Because if you take any function on xn, that means it's an element of C of xn, then it is determined by its value at each of those points. Then f is summation I equals to 1 to n f of I delta I. This is quite straightforward. And by the way, this delta I hope you know, but this delta I are the Dirac delta functions. So where delta I of j is 1 if j equals to I and 0 otherwise. So you can write any function on xn as a linear combination of this delta I, and this delta I is a linearly independent. That is easy to check. So C of xn is an n-dimensional vector space. Okay. Now C of xn is an n-dimensional vector space. So you and this alpha tilde is actually, it's a linear map, meaning it's like if you add two functions. So if you multiply this alpha, f by c, then this c comes out. And if you add two functions f1 and f2, then you can also check that this alpha tilde also preserves this addition. So this alpha tilde is the linear map, which means that it is sufficient to consider this alpha tildes on delta i's. If you know the value of alpha tilde on each of these delta i's, you know this alpha tilde on any f. So in particular, let us consider alpha tilde of delta I. Now, what is alpha tilde delta I? Alpha tilde delta I, by definition, is delta of so alpha tilde delta I is delta I of alpha tilde delta I, and then you have to act it on some j and sigma. Then this is delta I sigma inverse j. That is by definition of alpha tilde. The way we have defined alpha tilde. Now, the next step is, now on the other hand, see that this xn and sn, they are also finite dimensional spaces, right? And any function, any element, any function on xn cross sn, that can be written as a linear combination of delta function on xn cross delta function on sn. Because that is, as a set, this is actually, you can consider delta functions on xn cross sn, and you can also separate by the variable separation, you can do that. So in particular, see that you can consider this. So this is something which is probably goes a little bit further than the basic stuff that we have been talking so far. Here now we need to consider, we are going to consider tensor product. So yeah, if you are not familiar with the tensor product, tensor product of algebras, or tensor product of vector space. So this is basically like the only difference between a Cartesian product and tensor at this level. What we need is that if you have x tensor y then if you multiply with a constant, this is basically same as C x tensor y, and that is same as x tensor C of y. So this is something a very in a lame way, or probably in a very hand waving way, you can think about tensor product. But the motivation for, the reason for doing this is I want to see on xn I have a basis, I have fixed a basis. Therefore, I can also choose the basis for here as well. And then I want to see what elements do I get at the permutations. I mean, on the algebra of functions on the permutation group. So, which means that alpha tilde of delta I is actually a linear combination. This is by the vector space, by the vector space theory. So this is some j from 1 to n delta j, and here I have some functions u ji. So on this side, I am fixing again the basis of C of xn, that is delta j. But on this side, I want to see what are the functions that I get on this permutation. Now, let us do this simple computation, because we know how this alpha tilde looks like. So just we have to do the compare both sides. So this implies, so alpha tilde delta I acting on j sigma. Okay, maybe it was not a good idea to put j here, maybe put k. J sigma, this is same as summation k equals to 1 to n delta k. Now, this delta k tensor uki will act on this tuple. So that means delta k will take j as input, and uki will take sigma as input. So delta k of j times, because since they become complex value, so tensor disappears, so we see times tensor c. So this is ki taking value j. Now this implies that alpha tilde delta I j sigma was delta I sigma inverse j, and here what do we have? This k is a running variable, okay? So, but this condition delta k j, that is 1 if k equals to j. So that fixes k. So this means u j I actually, let me just write that u ki just a moment. Yeah. I did a mistake here. That's why it should be sigma. So this will be u ji and then sigma. Now this side is, so this implies that u ji sigma is, because here we have a delta function, and this function is 1 if I equals to sigma inverse j. So if I equals to sigma inverse j and 0 otherwise, which means I can rewrite this condition. See, I equals to sigma inverse j means sigma I equal to j. Now, what is this? Therefore, what is this uij? So uji, this means this is a function on Sn to C, well, actually R, defined by uji is basically the characteristic function with support Sn such that sigma I equal to J. So what basically this UJI does, it will pick a permutation and it only will see whether this permutation for a fixed ij, so you have j and I are fixed. So for every permutation, whether, so for a fixed ij, if you choose a permutation, it will only check whether that permutation sends I to j. If it does, then the value is 1. Otherwise, it is 0. So it is actually the indicator function for that permutation. I mean, for those permutations which just sends I to j. It doesn't care what happens to other elements. So that is what it does. So this finally means the group action that we have started with here, I mean, the canonical action of Sn on Xn that we have considered here, that defines a map alpha tilde of delta I, which basically goes to k equals to 1 to n, delta k tensor u k I, where u k i's are given by this. So you essentially replace permutations like the elements of the permutation group by these elements, essentially, algebra of functions. Now, what are the properties that we have for these UKIs? So, first of all, if you consider properties of U, let's say ij. So number one, if you take the summation over the first entry. Okay, maybe before that. Observe that Uij is same as Uij star. The reason is because Uij, they are actually characteristic functions. So they take value either 0 or 1. So therefore they are real valued. So their adjoint is same as the original function. And now that is same as Uij square. If you multiply Uij with Uij, then you also get Uij, where the multiplication is given by this pointwise multiplication, which I wrote here. So if you take Uij acting on, let's say, k, then by definition, this is Uijk times Uijk. Now, Uijk is non-zero if Uij, not k, actually sigma. So Uij sigma, Uij sigma. But Uij sigma is non-zero if sigma sends j to I, otherwise it is 0. So essentially it is actually easy verification that it is also, because again it's characteristic function. So it is actually idempotent, and Uij is same as Uij star. So this is basically a projection. Number two, if you take the summation over the first variable, what do you get? So let us compute this. This is actually quite easy. Summation I equals to 1 to n Uij, and you let it act on sigma, because this is a function. This sum will be a function on Sn. So this will be summation I to n Uij acting on sigma. Now, what is the definition of Uij? Here, actually, Ji, Uij will mean that sigma j goes to I. So, sigma j goes to I, then only it will be 1, otherwise it will be 0. And since sigma is bijection, this will happen only for only one Uij will be non-zero. All others will be 0 because sigma is a bijection. So this will essentially mean that this is 1 for any sigma. Similarly, if you take the summation over the second component, then also you will have this. But again, this will mean that by the same argument, since sigma is a bijection, this will also be 1. So this means that Uij is 1, or I mean identity function on Sn, or 1 in C of Sn, that is same as summation So these are the properties of Uij. And that means essentially what you are getting, what we are getting n square many entries from n square many functions on permutation group such that these conditions are satisfied. So now if you write it as a matrix in the matrix form, so if I call this matrix U, sorry, UN1, UN2, UNN. This matrix, so these properties, whatever we have here, this property says that each of the entries are projections. Sorry, there is a question. Sorry, I think there are two questions. I am sorry. So Uij times Uij is 0. Why? I mean, Uij times Uij 0 means Uij times Uij, you are claiming this is the 0 function. So, okay, let me, since there is a question, let me just compute it.
No, I mean Uij times Uji.
Uij times?
Uji.
Achha, Uij times Uji. Okay, okay. Uij times Uji. So Uij, so that means sigma, yeah, if sigma is not order 2, so okay, so Uij times Uji, so Uij, if you put it on sigma, that means sigma of j will be I, then the first one will be G1, but then for the second one, you have this sigma of I goes to j. Now, if you have both the conditions, if you want to satisfy both the conditions, that means sigma I equals to j and sigma j equals to I, which means sigma square I equals to
I.
Yeah. Yeah. That I mean, so yeah, you will get something on, I mean, depending on, but in general, I don't think you can say anything.
Okay, all right. So it's not that orthogonal projection kind of.
Row wise they are orthogonal, column wise they are
Okay.
orthogonal, because row wise the sum is 1 and the column wise the sum is 1, and since they are projections, so if you are in a same row, then they will be orthogonal.
Okay.
And if you are in the same column, they will be orthogonal. Yes, but if you choose from two different ones, then yeah.
So in a way, they are bistochastic, is it, Sutanu?
Yes, they are bistochastic. I mean, that is something which I learned very recently. Yes, in a way they are bistochastic. And in our quantum group literature, we call this as magic matrix. So magic unitary. They are unitary operators. So unitary matrix, that is easy to check. Now the question is it the identity for the group that we start? Which one identity? this sum over uij equals to 1?
Yes.
Okay, so that is basically, no, not the group identity. This is the, sorry, this is the identity element of Sn, function algebra on Sn. So this is the identity function on Sn.
Yes, sir.
So this is not the identity element of the group. No. Because right now we are not, so far we are not, so at the moment, I mean, up to this uij, we have not discussed anything on about the permutation group yet. We are just playing around with the the action that we have defined. I mean, this thing.
So sir, this is for the function that you define, no? This identity term 1 equal to, it is for the function that you identify, that we define Sn.
So this is basically, so one of, okay, so this one of Sn means it is the function which sends everything to 1.
Yes, sir.
The constant function, I mean, 1. Okay.
Yes, sir.
Okay. So yeah, okay. Now, if you just write this U as in a matrix form, then yes, that's that, as Rito Protoda also mentioned, that okay, this is basically, if you fix a row, it is, you can check that since they are at each and every element, actually they are projections. And I mean, projection means this the first condition. And the second, I mean, the second condition and second and third condition, rather, I just wrote it in a combined form. This basically says that if you take the sum over along the column or along the row at any, if you fix a row and take the sum of all the entries, you get 1. If you fix a column and take the sum of all those entries, you also get 1. Now, yes, I mean, if you just do some simple manipulation, in this case, you can check that row wise, if you multiply, if you take any 2 different entries, then they are actually orthogonal. And similarly, column wise also they are orthogonal in general. And this is basically, now if you consider the permutation matrix, like if you consider a permutation on n symbols, and if you look at its matrix representation, then it is basically if you fix a particular row, or so if you have 1, let's say at ijth entry you have 1, that means in the ith row or in the jth row you have all the other elements has to be 0. So that means if you take the, like, if you consider that this is the property of the permutation matrix, so it contains only one, I mean, it's basically like you have identity matrix and you are permuting it. I mean, 1 time, 2 times, or several times, whatever times you want to do it, and you get a permutation matrix. So this means this property, if you take the identity matrix, it says that, okay, only diagonal has 1 and other entries are 0. You can view this in the following way. Each of these entries are either 0 or 1. And at any row or any column, if you take the sum of those entries, you get 1, because only for diagonal matrix. Now, if you permute this, like if you permute their rows, you also, this property will remain same. And these conditions that we actually obtained by passing from algebra from the permutation group to algebra functions on the permutation group exactly gives us an analog of that. Now the next thing is what happens to the, now we have to consider the group structure. I mean, group structure means permutation group has a binary operation. What happens to that operation here? So the binary operation is a map from Sn cross Sn to Sn. Now, in the similar way, in this case, we will get a map from C of Sn to C of Sn, tensor C of Sn, actually C of Sn cross Sn, but then I identify this with C of Sn tensor Sn. And then what we are going to do is, so it is sufficient to check what happens to this, I mean, because we are interested now on this on these uij's. So we want to understand what happens to uij's. I mean, instead of any function on Sn, so delta of uij, and if I consider a permutation sigma, so sorry, so okay, let me just tell you the formula for this, because this will take, I mean, one can do this formally, but this will take some time. So if you actually, so in order to get this, in order to get the delta on uij, what you have to do is you have to do the following. You have to go to the group action here, the one that we have defined here, the action of Sn on Xn. We have to look at this action, and then what we have to do is we have to consider this alpha tilde and see what happens to the because so here what we had is, here we, if you take sigma 1 sigma 2 here, then actually the composition of two permutations are coming out as, in a sense, composition of alpha twice. I mean, in a sense, not composition, but you have to apply alpha twice properly, I mean, in an appropriate sense. So similarly, at the level of algebra, what you have to do is you have to compose alpha tilde twice, I mean, apply alpha tilde twice, and that will correspond, I mean, on one side, and the other side you will get actually this this delta. So if I just want to draw the commutative diagram, so the diagram, I mean, this delta is characterized by this commutative diagram, that this is C of Xn to C of Xn tensor C of Sn. This is alpha tilde. Let me just make some space here. And then you apply identity tensor delta here. This will be C of Xn tensor C of Sn tensor C of Sn. And on this side, you apply alpha tilde, that you will get C of Xn tensor C of Sn. And to I mean, on this you have to consider this map. Now, if you just compute these alpha tildes, then essentially the solution delta will be characterized by this commutative diagram. So now, okay, so that's how you actually get this thing. And one more important thing is that if you observe the formula for delta, this is like matrix multiplication, because if you replace this tensor, this is just idea, I mean, just as an analogy. If you consider this tensor by just multiplication, like, then you have uik times ukj summation over k, that gives you ij. So in a sense, you are dualizing the matrix multiplication map in a sense. So that's how. So in a sense, this is not something far from the group operation and so on and so forth. So in summary, what we have is that we view Sn as C of Sn and delta. So we have replaced this. So maybe it is better to write this C of Sn with the binary operation. So we replace this Sn by algebra of functions and this binary operation by this delta. And this pair we call, so this pair is actually the way we have constructed. We have actually argued or discussed that we can view permutation group. Just, we don't actually have to consider the set itself. We can do everything at the level of algebra. like algebra of functions on the permutation group, and the binary operation is preserved by delta. And there are more properties, by the way, like there are some properties of this delta will satisfy and so on and so forth. And now, based on this observation, I mean, this is basically the black box for this idea of quantum permutation group. So, but what is still classical about this? The classic still classical means, of course, we have started with a group and then we have constructed this C of Sn. But now this algebra is commutative, meaning this is algebra of functions on n points. So this algebra is still commutative. So now what Wang did, this is quantum permutation group due to Wang in 1998. What he did, he considered U is basically this, and I mean, like he considered n square many elements. Elements means, well, if you want, you can view them. You can consider them as bounded operators on a, I mean, on a Hilbert space, such that Uij star is Uij square, number one. Number two, the same condition that we actually got. So you consider, I mean, in short, you consider a bistochastic matrix or magic matrix, and you consider the algebra generated by these relations. One more thing, by the way, this is something which I should mention here, that Uij UKL commutator, this is 0 for all Ij KL. Because these Uij and UKL, they are functions. They're not anything else. They are functions. So they commute pointwise. So if you compute their commutator, they has to be 0. Now here, you don't assume that, which means you are actually passing from a commutative algebra to a non-commutative algebra. So now you consider an algebra generated by these elements. Okay. By the way, this is just algebra. I mean, I'm not taking closure or anything. This is just the star algebra generated by. I mean, well, star is redundant here, at least because Uij star is Uij. So you consider algebra generated by. Yeah, I mean, you consider the star algebra generated by this Uij. That means you will consider polynomials in n square variable, and now those variables, instead of those variables, you consider this Uij, and when you satisfying these relations, and when you multiply them, you have to also take care of these relations accordingly. So this is basically, so consider the star algebra, complex star algebra, more precisely. Generated by Uij and subject to the condition 1. And then what you do is you consider this delta Uij the way it was done for, I mean, for the classical, I mean, for the permutation group Ukj. Now you have to check that this delta is well defined, meaning this delta Uij also satisfy these relations. Then you can show their exist by the universal property. So, I mean, so okay, I must say universal complex star subalgebra, of course. Otherwise, yeah. So then by universal property, you know that this delta is well defined. So this, so you consider, so now if you name this algebra, the complex star algebra denoted by C of Sn plus and delta, then C of is called the quantum permutation group. I will say algebraic, because this is still, I mean there is no closure. Algebraic quantum permutation group, because, and now if you, because since these I mean, now if you consider these as, I mean, if you consider Hilbert's representation of these operators, then these two conditions ensure that your operators are bounded, so you can consider the universal C-star algebra generated by them. So that means, essentially means that you have to take the closure of this with respect to the universal C-star norm, and then you will get a C-star algebra, and that is called the quantum permutation group. Now the question is whether this is different from, because what is the difference between the ordinary, I mean the permutation group and this quantum permutation group, is that in the ordinary permutation group, we assumed, I mean it was not assumed, it was actually followed, that the algebra was commutative. In this case, we don't know. So the natural question is whether this algebra is always non-commutative. It may happen that this relation essentially forces the algebra to become commutative, by the way. So now that is the most interesting part. So consider case by case. So if n is 1, that means if you have only 1 point, then obviously you can check that well, for 1 point, then there is only one unitary, I mean one uij, and that is basically uij star is uij square, and so on and so forth. So for 1 point, there is nothing much you can do. So for 1 point, this is essentially commutative. For 2 points, so for n equals to 2, what we have is we have this 4 elements. Now they satisfy these relations, these relations. But now let us try to see this row sum column sum. If you fix a row, then the sum is 1, which essentially means that this u12 has to be 1 minus u11. And similarly, if you fix this first column, this will say that this u21 has to be 1 minus u11. And now, if you consider this row, the second row, this will say that u22 has to be u11, which means that if for n equals to 2, u12, u21, u22, all of them actually are either u1, I mean they are u22 is 11, and u11 and u21 is actually 1 minus u11. So this means this is essentially generated by a single element. So C of Sn plus is actually commutative, and this is isomorphic to C of Sn. So for n equals to, you get commutative, and not only that commutative, you only get this permutation group. For n equals to 3, of course, this is not as simple as this, but using this type of argument, it can be shown that C of Sn plus is isomorphic to C of Sn. So for n equals to 1, n equals to 2, n equals to 3, we are not getting anything non-commutative. We are still getting the classical one, classical permutation group. But from n equals to 4 onwards, we have something fascinating. So for n equals to 4, this is non-commutative. commutative and infinite dimensional as well. Question is how to prove that. Actually, this is for n equals to 4 onwards, but let's say for n equals to 4, how to prove that? So for n equals to 4, what you have actually 16 elements, like 4 cross 4 matrix with the property, with these properties. Now the question is, if you want to argue that this algebra is commutative, non-commutative, that means you have to, if it is sufficient to show that there exists at least 16 elements satisfying these properties, and they are at least any two of them do not commute, then you are done, because this is universal algebra generated by these relations. So for that matter, what you can do is you can choose your elements in the following way. So let P and Q are non-commuting projections. This is something you can easily construct. So for instance, consider infinite dimension also. For instance, you can consider C2, and you fix the basis for C2 to be 1, 0 and 1, 1, let's say. And now consider the projection. P is from projection on 1, 0, and Q is projection on 1, 1. And then you can check that they do not commute. So there are plenty such project. I mean, you can find a lot of example projections of this sort. And now you actually construct this matrix in the following way. Now observe that they are projections. So if P is a projection, then 1 minus P is also a projection. So each of these entries are self-adjoint and idempotent. Now, if you consider the row sum or column sum at any stage, they are 1. And most importantly, they do not commute because P and Q do not commute. So this algebra is non-commutative for n equals to 4. Now for n equals to 5, what you can do is you can just do the same thing, and then just for 5 onwards, you just put this block matrix in one side, and then rest you can put anything. I mean 1, 1, for instance. So this shows that from n equals to 4 onwards, the quantum permutation group is much bigger than the permutation group. And by the way, the permutation group is a quotient. So also furthermore, C of Sn plus to C of Sn. So furthermore, there exists a quotient map. The reason why this quotient map exists, because what you do is you have these conditions, and on the top of it you quotient this. You actually quotient by the relation that okay, Uij commutator relation. If you impose the commutator relation Uij UKL is 0, then you get a quotient map from this. And if n equals to 1, 2, or 3, then we have argued that this quotient map is actually an isomorphism. So this means that this quantum permutation group for n equals to 4 onwards is much bigger, which means that there are more symmetries of finite set with 4 or more than 4 points than which cannot be captured by the classical permutation group. You have to actually go to something called the quantum permutation group. And in those cases, these entries Uij, you can call them as quantum permutations. I mean, they are analogs. So in the beginning, when I started, I said that okay, quantum in our context means that it is just non-commutative and infinite dimensional. That's what actually the agenda, more or less. So here, what I sort of tried to convince you that if you take if you consider symmetries of 4 points, a set which contains 4 points, then you may not be able to capture all of them, because in other words, there can be some symmetries. Because classical, the way we actually talked about symmetry. Now, it's a question, by the way. This is something which I will not be able to discuss in this talk. What is the meaning? What do I mean by quantum symmetry? That is something one has to mention. But even without mentioning that, so what I sort of the way I constructed is that for permutation group, if I just motivate myself from the perspective of permutation group, then just by relaxing the condition, the commutator 0 condition, I get something non-trivial from 4 or more than 4 points. And the question is what exactly this means. How do you interpret this? This was interpreted by Wang, of course. He actually said that, okay, he actually actually it's not him. It was this idea was there even before he came up with this with his work. He published his paper, but his results. But before that, this idea was there. What is the meaning of quantum permutation? So quantum permutation roughly means that if you have a compact quantum group which acts on a finite space, then you can say roughly that, okay, it's a quantum permutation. And what, in that sense, these quantum permutation groups are quantum symmetries of finite spaces. And in that sense, that is why these objects, this algebra with delta, this is called a quantum permutation group. And the moral of the story is, it seems that if you generalize the notion of permutation, generalize the notion of symmetry, meaning if you replace a group by a quantum group, compact quantum group, more precisely. So far, the existing theory is well behaved with the compact quantum group. Then you can actually get something which is an analog of permutation group. And this is much bigger, much larger than the classical permutation group. And this has many applications, by the way. This was like, to be honest, this was the beginning of the study of quantum symmetry, which I which I started learning very recently, meaning like from last 2 or 3 years, probably. And this has many applications. One of the simplest application I can quickly tell is, if you take a graph and if you, let's say, undirected without any loop, the nice graph, let's say, and if you want to compute its automorphisms, meaning set of all maps, graph homomorphisms from the graph to itself, So you consider set of all maps from the graph to itself, which will map edge to edge and vertex, and it will preserve the adjacency. Meaning, if you if you have two edge E1 and if you have two vertices E1, V1 and V2, and if you map it to, let's say, W1 and W2, and if there is an edge between these two vertices, that should also go to the edge should be also there. You cannot destroy the graph structure. It should preserve the graph structure. Now you know that if you have a graph, you can encode the graph in terms of its adjacency matrix. Now, automorphism of a graph, finite graph, of course, I'm talking about finite graphs. If you have a finite graph, then the automorphism means you consider. So if you have a graph on n vertices, that means an automorphism is a map from n. It's a map on n cross from n a set with n points to a set with n points, right? Which means that classically also for graph automorphism, if you know about them roughly, they are actually quotients of permutation group. So you actually consider the permutation group and plus some relation. Now in this case, if you want to consider quantum automorphism of a classical graph, what will be the idea? The idea is you consider this matrix Uij, and then you say, okay, this is generated, the underlying algebra is generated by Uij, which are magic and everything, and it will commute with the adjacency matrix. if you consider a graph and if you say that adjacency matrix is D, then you simply say that, okay, this is, you satisfy these relations, I mean, this magic. On the top of it, you also assume this relation. And that will give you an automorphism, notion of quantum automorphism of a finite graph. And in this way, there are many examples. I mean, it is not always the case that, so, and in this way, actually, the definition, this definition of quantum automorphism of a graph goes back to Theodor Banica. And using this definition, they constructed, there was a huge development actually occurred in the area of quantum symmetry of classical graphs. And the question is, given a graph, can you talk about quantum symmetry? And they constructed many interesting examples of quantum groups, genuine quantum groups, meaning not groups, but quantum groups, which actually comes from quantum symmetry of graphs. So for instance, there is something called hyperoctahedral group, and then there is a version of hyperoctahedral quantum group. This is just an example of graphs, and there is a quantum version of that as well. So yeah, and as you know that if you have an object which is a finite type, meaning there are finitely many points, and if you want to compute its symmetry in whatever sense, whichever sense you want to, then you have to go through the quantum permutation. I mean, you have to go through permutation group in the classical case, meaning in the ordinary symmetry. In the quantum case, it is also similar. You have to go through the quantum permutation group. And yeah, very recently we have generalized this idea, the notion of quantum permutation group towards braided quantum permutation group, but that is something not difficult, but conceptually that requires some more I would say, I mean, notations and ideas before I define what is the meaning of that. And so, but this is something very recently we have done that. And but yeah, if you're interested to study quantum symmetries or something, then I think the first thing should be actually Wang's work, actually quantum permutation group. And yeah, many interesting examples of compact quantum groups appear as quantum permutation group. Not always, but in many cases. So yeah, I think that's all I wanted to talk about, and I hope I at least, I mean, as I said, like, I mean, I didn't want it to give only present results and theorems. Instead, I wanted to motivate the idea, and I hope this was useful to some of you. I hope that will be good. And yeah, that's all for now. So yeah, so thank you. And if you have any question, you can ask me.
So thank you, Sutanu. I think there is at least one question in the chat box, if you can open it.
Yes. Okay, I don't know the answer to this. No, I don't know. Let's not comment, because I don't know.
Also, I think Bhubaneswar has raised his hand. I can see. He can say something. Or it's a by mistake, I'm not sure. Bhubaneswar?
Connecting to
Yeah.
audio.
Yeah, I think it is raining very heavily here, so probably he is having some difficulty.
Hello, sir.
Yes.
Actually, we are just comparing with permutation group and quantum permutation group. So
Yes.
in in general sense, what we know about quantum, like in physics, we are just defining quantum as probabilistic function or probability density function. So is there any notion or any connection with this group with that quantum?
In a sense, yes. I remember seeing something similar, but I don't know them by heart. But let me just okay, it's here. So let me just tell you a reference where you may find this. I have to, because I bought this book very recently. This is a new book by Theo Banica, and it's available. It got published very recently in January. So in this book, I remember of, I mean, I have seen the how do you say, the preprint of these topics on archive from last 2 years or something. But in this book, yes, I mean, there are some chapters where actually some quantum probability is done, and some references, I mean, something also mentioned about them. So yeah, so for instance, yeah, these chapters might answer your question, might not, I don't know. There is a chapter called like laws of characters and truncated characters and free probability and stuff. So but essentially I think what you are asking is quantum density matrix kind of thing, whether it's known in this context.
Yes. Actually, the way you have defined the functions, like if we take it as a commutative operator or non-commutative operator, it's behaving like the same, at least for the n equal 2 case. And the way you have defined the algebra, like I was checking the properties, the same Pauli matrix has also the same properties.
Yes.
So that's why I am asking.
Yes. So see, for n equals to 2 or 3, I mean, for up to n equals to 3, it is not that, to be honest, from the perspective of quantum groups or non-commutative geometry, they are boring because they are commutative. But yes, what you are saying is correct. And I mean, the thing is, on quantum permutation groups, many things has been done. Many means a lot. So I'm sure something in the direction that you are asking is also known, at least something. If you look in the context, I mean, so I think the best place to look for such things will be, I think, free probability and quantum permutation group.
Okay.
In that aspect, you may find something, and I'm sure there exists something, but I mean, I don't know, because yeah, sorry about that. Yeah, please continue.
And sir, we are talking about quantum symmetries of finite spaces. So if I take the quantum permutation group in finite spaces, so as
Yes.
permutation group has cardinality, like for Sn it's n factorial. So at least for 2 and 3, can we compute the cardinality of quantum permutation group?
Well, see, the thing is, so the cardinality for space corresponds to the dimension of the algebra. Because because if you take just think about this. So if you have a set with n points, the way we have defined, I mean, the way we have, I mean, I presented today. So you replace the set by algebra. Oh, what happened? So yeah, we replace the set by algebra functions on the set. Now, if the set has n points, then the algebra functions as a vector space, it has dimension n. So the cardinality gets replaced by dimension. Now, for n equals to up to n equals to 3, it turns out the dimension of the algebra is factorial n. But from n equals to 4 onwards, this is infinite dimension. So there is no notion of cardinality.
Okay, and another thing, can you please explain once again what is the exact difference between permutation group and quantum permutation group? Because in quantum permutation group, it is infinite dimensional and
Yes.
non-commutative, or maybe commutative sometimes, or like always.
No, if it is no. If it is commutative, then it will be finite dimensional.
Okay.
In this case, not always, but in this case.
But for permutation group, like from S3 onward, it's not abelian.
No, abelian in this context, see, I mean, okay. So what you are saying is, see, the abelian, okay. No, actually, see, I mean, the thing is, once you replace the, okay, the way we have done, again, so we started with permutation group, and then we replaced the permutation group by algebra of functions. Now, algebra of functions does not see the group law just as an algebra. Algebra of functions is given any set, you can define algebra of functions. But if
Okay.
you want to see the group law, maybe whether that is abelian or not, then you have to go to the dual group, dual of a quantum group. So you have to, so if you have a group, then the corresponding, if you have a finite group, let's say G, then the corresponding quantum group is CG, some structure on CG, algebra of functions. Now, if you want to see whether the abelianness or not, whether the group is abelian or not, then you have to go to the dual. And the dual, the reason why you have to go to the dual is because consider the L1 functions on G, where the product is defined, I mean, given by convolution. In order to define convolution, you need the group law.
Yes.
And the convolution is commutative if and only if the group is commutative. So you have to go to the dual, and in the dual, because at the level of CG, the multiplication is defined pointwise. So it doesn't see anything on the group, it's just the set. But if you go to the dual, then the multiplication is defined in terms of convolution. And there you can see whether the group is abelian.
This is the same way like you have defined with Dirac delta function as a in the form of linear functional, right? At the very beginning.
No, but Dirac delta function. So in my talk today, I didn't say anything about the convolution, by the way. I didn't say anything. Dirac delta function I took as a vector space basis. Also, I considered the multiplication of Dirac delta functions as pointwise. I didn't consider the multiplication of Dirac delta as convolution. But if I do, for instance, I mean, on Xn I cannot, because Xn has no group structure. But on permutation group, if I do, then I get some, whatever I will get is basically the group ring on Sn. And the group ring on Sn is non-abelian, unless your Sn is non-abelian. I mean, it is abelian if and only if Sn is abelian. But but if you go for the dual of quantum permutation group, then probably the group ring doesn't appear actually. That is the point.
Okay, sir. Thank you.
Okay.
Biholanda raised his hand.
Yes.
Yeah. Thank you very much for this wonderful talk, first of all. So I would like to ask that every bistochastic matrix is, I mean, it can be written as a convex combination of permutation matrices, right?
Okay. I don't know that, but okay.
Okay. So I just want to ask that is there any quantum analog to this result?
No, the thing is, so okay, can you recall the definition of a bistochastic matrix?
So it's a row sum is one and column sum is also one. It takes a probability distribution to a probability distribution.
Okay, and you don't have any condition on the entries, whether they're self-adjoint or anything?
But I'm talking about the classical thing first. I mean, it's just non-negative numbers.
Non-negative numbers. So you are not assuming that they are. So you are not assuming that they are actually like. See, classically, okay. So you are saying that bistochastic matrix is a convex combination of quantum
permutation matrices.
Permutation matrix.
Birkhoff-von Neumann theorem. This is sometimes is called.
Right. Okay. So that means you are not considering the entries to be projections.
Projections, right?
Right. Okay. So in the quantum case, yeah, as I said, like I very recently I actually came across this notion of bistochastic. I didn't know about them earlier, but yeah, I think if you consider this UIJs, this matrix UIJ, you can consider this UIJ to be the quantum permutation matrix, and then probably you can consider. But the point is. But the point is, you can always write down convex combinations of this, but see, essentially.
Yeah, may I say? I think, see, here the different examples are in different algebras. So the convex combinations
Yes.
don't make sense.
Okay.
Okay.
Yeah, yeah. I mean, I wasn't familiar with this concept and bistochastic, but okay. No, but Rajata, what do you mean by? I mean, because okay, because since I am also not familiar with this,
No, I'm saying if you have two different examples of this kind of double stochastic things here,
yeah.
they belong to different sister algebras.
Okay.
Between them.
Right.
So,
Right.
whereas earlier we had just all positive real numbers, so you can talk about their convex combinations.
Right.
Okay.
Right. Yes. Thank you.
Thank you very much. Thank you.
Any further question?
Yeah, but if you have any further questions or any ideas regarding this, let me know, because there are many things which is known about quantum permutation groups, but as I said, I mean, it will take some more time to understand them, for me at least. Yes.
Sir, do we know the exact operation that the group operation we are performing for the quantum permutation group here?
Okay, first of all, let me say this: quantum permutation groups are not groups. First of all, and the group operation, if you want to know what is the group operation, I mean the analog of the binary operation, not exactly the binary operation, but the analog of the binary operation, that is basically given by this delta uij. So you can define this delta at the level of algebra as well. This is actually an algebra homomorphism. So yeah, this is the analog of group of, I mean, analog of multiplication map for for a group, and that's why this delta is called the co-multiplication map.
And
So,
sir,
yeah.
what is the identity element for the quantum permutation group?
See, the thing is, if once you have a group, see, okay, once you have a group, so the way, once again, the way I have motivated this whole idea, you start with permutation group and then you replace the permutation group by algebra of functions on the permutation group. So once you replace that, then everything, so this elements on the group and everything actually gets I mean, like, disappears. But yeah, so the point is, since you raised this, so let me just quickly mention this, that so the identity element for any group, so in this case, this identity can be I mean, if you consider the identity element and consider the subgroup, this is basically contained in Sn. So this gives a map from C of Sn to C of this identity, which is singleton, which is essentially means algebra of complex numbers. And the way it is defined is epsilon of any element. So epsilon of any permutation is basically evaluation at identity. So this is called the co-unit map, by the way. And so that means, so this is, by the way, for the quantum, for the permutation group. Now in this case, in case of now, you can also check that this epsilon uij, because we are not interested in on arbitrary function, we're interested on epsilon, I mean, uij, that is nothing but delta I comma j. Meaning, if I equals to j, then epsilon is 1, otherwise it is 0. Now, this same formula also also exists at this on this algebra. So you can prove that this epsilon of uij actually extends. I mean, this is an algebra homomorphism on this algebra. But the problem is that actually, okay, it actually also exists if you take the closure. Here you are taking the maximal closure. I mean, like the universal sister. I mean, you are taking the maximal closure. So yeah, universal sister algebra. So this will also exist at the level of sister algebra as well. But yeah, so the identity element for the group corresponds to this function, to a function from C of Sn to C, and that is given by on uij, that is given by delta ij. So that means it sends ii to 1, and to the rest it sends those elements to 0. So it corresponds to the diagonal matrix 1, 1, 1. I mean, is it okay? Sorry, am I audible?
Yes, sir, you are audible.
Okay, okay.
Yes,
okay,
yes.
okay.
Sure.
So I think there are no more questions. So thanks, Sutanu sir, for this wonderful talk.
Thank you. Thank you so much.
Thank you, sir,
Yeah.
for the
Thank you.
Thank you, Sutanu.
Thank you.
I hope by next semester we will have better situation and we can call you here.
Yeah,
physically.
yeah. Of course, I'll be happy to go to
Yeah.
IISER.
See you then.
Yeah. Thank you.
Bye.
Bye.
Bye, sir.
Bye.